ladies and gentlemen, again, also from my side here at Lauterbach in Hohenkirchen-Sigelsbrunn. I first want to introduce myself. My name is Alexander Merkle, and I will talk to you today about the topic of multicore debugging. Multicore itself is used, multicore architectures are used since many years with high-performance application processing systems, for example, desktop workstations and so on. And now this topic becomes more and more a topic also in the embedded systems, not only to increase the performance of the system, but also for energy saving issues or other issues, or timing issues. So with multicore, we distinguish between two different schemes. So first we will talk about the AMP and the SMP scheme. I will give you a short introduction what's AMP and what's SMP. After that, I will give you a short introduction how multicore debugging itself works within the chip. How do we, as a debug solution provider, work with your chip, and what requirements do we need from the outside, do we expect from you to implement on your board. Later, we will have a closer look to AMP and SMP debugging in detail with TRACE32 PowerView. So let's start with AMP and SMP. Classically, you had on your printed circuit board a single chip. This single chip had a single core inside, and the single core had a data and address bus. And what was attached to this data and address bus was peripherals, data memory, and instruction memory. For classic systems, it was ensured that the master core, so the single master core, had exclusive access to the bus, to the peripherals, and to the memory. If we look to the software side, we had an operating system, and this operating system assigned the tasks, which I show you here with this little tower, in a time-sliced manner to the core. So, which means that at each point of time, you have got a single task which is executed on the CPU. And the task itself will then be executed after each other by a specific scheduling scheme you select by your operating system. Okay, this is a single core chip. This is not yet multicore. Let's talk about multicore. Simplest solution to implement a multicore chip is simply to add a second core. I will do this here. We have now again one core, another core, and we have still got our bus, peripherals, data, and instruction memory. But this time, these memories are no longer exclusive for one CPU. They are shared. So what might happen is that you get on your chip, you get for each core not only the shared bus, but you might also get privately owned memories, privately owned data memory and instruction memory, and also privately owned peripherals. On the last slide, we saw our single task set. Now, I'll show two of them. Why? I've got two cores, and in principle, they don't need to know from each other. So, the first core can have an operating system, for example Linux, and assign his tasks to his core. And the second one could be, for example, a real-time processor, which has its own tasks. And what we finally get from the operating system point of view, you have got a concurrent execution. You can assign one task of this task set to the left-hand core, and you can assign a different task to the right-hand core. So you get a concurrent execution of multiple tasks, but you cannot interchange these tasks of each other. So let's sum this together. AMP stands for asymmetric multiprocessing. Asymmetric means we have a heterogeneous system. We might have different core types. A classical setup would be we have a CPU, an application processor, plus a DSP. Or we have different core types. We have got an application processor and a low-power CPU, or a real-time CPU, which is used for highly deterministic interrupt handling. We also might have multiple chips. On the last slide, I can cut this in the middle, and here again, and this would be our shared bus on the printed circuit board. On the left-hand side, we have chip 1. On the right-hand side, we have chip 2. So AMP debugging could be also done in multiple chips. What arises from this is that the CPUs don't need to be instruction compatible. So they don't share their code and data. This is specific for AMP system. And we have each core of an AMP system has its designated task set, which means we have two operating systems that are not coupled together. One operating system does only know about his cores, and the other operating system does not know from the other. So let's have a closer look to one specific case. All cores of our system are of the same architecture. We have a dual or a quad-core CPU in which all cores understand the same instruction set and they have the same access to code and data. I will show you here an SMP example. We still have got one chip now. We have one core and another one. And these two cores, they share now one common system bus. They share their memory, their data memory and instruction memory, and they share their peripherals. The advantage of the SMP case is now that we have, as we can assign tasks, the task is a piece of code which is executed on the core. We can assign now this task either to the left-hand core or to the right-hand core. So we can use our scheduling scheme to load balance our single task set to the cores and to assign dynamically to the task either to the first core or to the second core. This is done by the operating system. So in this case, the operating system is aware of all cores of your system. It knows about all CPUs in your chip. And what we get is also a concurrent execution, like in the AMP case, but this time of one single task set. So SMP means symmetric multiprocessing. Symmetric, why symmetric? It's homogeneous. All cores of your chip are of the same architecture. They understand the same code. They have access to common memory as well as data as well as code. You have a common task set, and your single operating system is in charge to assign tasks to your cores. Yeah. So how can I detect whether I have got an AMP case or an SMP case? We saw this key facts on the last slide. I show you here a simple condition graph. If your cores are all of the same architecture, they understand the same they have the same instruction set, they understand the same code, you might have an SMP system. This isn't hardware specific. The second case, you have a uniform memory access, which means it is ensured that at every point of time, both cores access the same memory content, which is a problem, for example, if you use caches in the chips. So the chip must support uniform memory access. And last but not least, the software condition is you have got a single operating system which manages all cores of your chip. Then you can use it as an SMP system. Otherwise, it will be definitely an AMP system. Okay, this was it for the AMP and SMP introduction. Let's talk about debugging itself. On a printed circuit board, you can populate multiple chips. I've done this here for you. I've got on the left-hand side chip, and on the right-hand side, another chip. Both chips are shown in light blue. And within this chip, I can have one or multiple cores. So on the left-hand side, I added 2 cores, 2 CPUs. So I've got on the left-hand side a multi-core chip. And on the right-hand side, I've got, for example, a special processor like an DSP. So this CPU is not compatible, this DSP is not compatible with this CPU. On your printed circuit board, you normally chain the cores, which means you're using JTAG. JTAG has got one data line, one control line, one clock line. And you simply connect one core after each other in a line structure. So what you get from this is a so-called daisy chain. You connect the debugger to the left-hand side, and it communicates through the first core, second core, the first core of the second chip, and then it goes back to the debugging unit. So the debugger, so the single debug box is now capable to communicate with each core in your system. Internally, it looks like this. This is again first chip, second chip. Keep in mind, these two are the CPUs, and this is the DSP. How it works internally is quite simple. It's a large shift register. The debugger sends data in here. It is first comes into the first core, then to the second core, then to the third core, and comes then back out again and is sent to the debugger. So what is interesting for the debugger is the length. I've got here, first CPU has a width of 4, second also a width of 4, and the DSP has a width of 7. So in total we have 4 plus 4 plus 7, so 15. So the debugger needs to know the length of the chain. But how can he communicate with a single core in the line? It's quite simple. When you want to communicate with this one in the middle, we know the total length is 15. So I've got 7 bits to the right, 4 bits to the left. We are talking about the so-called pre- and post bits in the chain. Down here I show you our system config dialog, where you can adjust these settings. It's the same mapping as here in the picture. The post bits, why post bits? Remember, we shift in from the left. So these bits we shift in first will connect to this core, so it's pre, and the ones we shift after this one are the post bits. We adjust them here. We have still the total length of 15. The debugger knows from the CPU selection about the width of the middle core we are currently going to debug, and we have got the same mapping, 4 and 1, and again 7 and 1. But another question which might arise, when it's that simply one line, the debugger doesn't know about the chip and core information. Is this information necessary for us? Yes. We switch back again to the old view. We have got again one chip, another chip, one chip with 2 cores, one chip with 1 core. Is this chip and core information necessary? I say yes. The cores might share common peripherals, like for example on trace port. They can share their data and address bus, or they might have specific hardware accelerators that can be only used exclusively. So what we need to know is the core and chip index. I'll give you here an example. So the red core would be for us the second core of chip 1. Sorry, it doesn't work in that detail today. And on the right-hand side, we have the second chip, first core. It's for us core 1 and chip 2. And from this mapping, we know about we know whether your cores are in one chip, they might share peripherals, or we might combine things together or not. last but not least, we have the shared signals of the JTAG protocol, which is highly critical, is reset. Up here, I've combined together JTAG, which is the data lines and the control line, TDI, TDO, and TMS. And additionally to this line, the JTAG protocol has reset lines. Task reset, which is the reset signal for the debug port, and system reset, which is like, for example, your reset equivalent to the reset button on your printed circuit board. System reset as well as task reset are shared signals, which means system reset affects both cores of my chip. Task reset also affects both debug logic of both cores of my chip. So you might imagine you start debugging your first core. Previously to this, you reset your system. After that, you connect to your slave system. What will happen if you reset again? You connect to this one, we reset again, we swear out the master core again, and we reset it again to the whole system. So we need to know about this, and for this reason, we automatically configure or pre-configure the so-called slave bit. It's also shown down here, again, in the system config dialog. It's named slave. It's automatically configured, but if you want to wrap your configuration, you're also allowed to change this bit. So let's sum this all together. JTAG is capable to communicate with each core and each chip on your printed circuit board by daisy chaining, which means you connect all cores, all chips in series. The chip and core information is still required by us to handle shared resources. And only one debugger, we call this the master debugger, is allowed to reset and to initialize initially the printed circuit board, all parts of your printed circuit board. So let's come to this situation. AMP, asymmetric multiprocessing. Keep in mind, we have got might have a heterogeneous system. So the instruction set, the disassemblers, the data and address bus might be compatible, different in this. We might have two completely different types of CPUs. What I show you here is a snapshot of our TRACE32 start tool. With this tool, you can configure your debug setup. What I've done here, I've got here on Power Debug 2, you heard in the last presentation by Ms. Hu, connected by USB. And what I do now is I assign to this USB debugger two debug drivers, two PowerView instances. One for the ARM instance, I will later use for the first core of my chip, and one for the DSP, the second core of my chip. So I assume now here that I have one chip with a CPU and a DSP. Again, what is master and slave? The master is the first instance I use to connect and to set up my system and my chip. So simply by clicking here, we start the master instance. And this instance is the first instance which is running now. And this is in charge, again, to reset the system and to initialize debug peripherals. The slave instance is not started at the beginning. I will come to this later. Why? Might be your chip is still in power saving mode or in a kind of power saving mode. Typically, when you have a modern multiprocessing chip, you have got one master core and some other cores. We call them here slave, because in most cases, and because of power efficiency reasons, only one core starts, and this core is in charge to initialize the chip from the software point of view. And the other cores might be either held in reset, they might be clock gated, or they might be simply powered off. So what you need to do in hardware is, by this master core, to set up the other cores of your chip. So, and you need to do exactly the same with the software. You cannot attach at the beginning to a slave core which is still held and reset by hardware, or which is clock gated. You cannot, it doesn't work. Finally, what we get is a multiple GUI. Is that we have multiple TRACE32 windows. I'll show you here 3 of them. And each GUI here is in charge for one core of our system, or for one set of cores. What is most times quite useful is synchronization. So for example, when you want to start, for example, your ARM application processor, you also want to start your DSP. And vice versa, when you stop your DSP, you want to start your ARM application processor. So what we support is